everyone, I'm Janvi, and today in this video I'll be walking you through 4 problems from transport phenomena. The 4 problems are: the first is double pipe heat exchanger with increased flow rate. The second is gas phase reaction volume in a PFR. The third is cuvette flow with viscous dissipation and variable viscosity, and the fourth is heat transfer between two porous plates with air blowing through it. So let's start with the first problem. The first question says oil is cooled from 60 degree to 40 degree Celsius in a pipe of double pipe heat exchanger. The cooling water flows countercurrently to oil with inlet temperature as 15 degrees Celsius and outlet as 35. The oil tube has inside dia of 22 mm and outside dia of 25 mm with inside and outside heat transfer coefficients given as 1600 and 1400 watt per meter square Kelvin respectively. So we have to find out the exit temperatures of both oil and water when the oil flow rate is increased by 40%. So here we have the given data, and first we will find the overall heat transfer coefficient. To find it, we will use this formula: 1 by U equal to 1 by inside heat transfer coefficient plus inside dia upon outside dia into 1 by outer heat transfer coefficient. So using this formula we get U as 435.5. Next, since delta T for both hot and cold fluids are equal, the heat capacity rates will be equal. So this tells us that this is a balanced heat exchanger and the heat capacity rates are equal. We get CR as C minimum by C max, which is equal to 1. Next, we will calculate LMTD. Since delta T1 and delta T2 both are same, we'll use L'Hopital limit. Using that we get LMTD as 25 degrees Celsius. Next we'll calculate effectiveness. So epsilon equal to Q by Q max, which is equals to 20 by 45, which comes out to be 0.44 for a counter flow, with CR equal to 1 and NTU equal to epsilon upon 1 by epsilon upon 1 minus epsilon. We get NTU value as 0.8. So for 40% increased flow rate condition, we'll find the new NTU value. For new NTU value, it is given that the oil flow rate increases by 40%, resulting in increased value of CH by factor of 1.4. Since UA stays the same, the new NTU is 0.8 divided by 1.4, which is 0.571. So we get new NTU as 0.57. Also calculate the capacity ratio, new capacity ratio. Since CH has increased but CC is same, the new capacity ratio will be 1 by 1.4, which is 0.714. After getting capacity ratio, we'll find new effectiveness. The new effectiveness will be using this formula, effectiveness formula, which is 1 minus e power minus NTU into 1 minus CR whole divided by 1 minus CR into e power minus NQ into 1 minus CR. We get new effectiveness as 0.378. Next, we calculate the new exit temperatures using the formula Q equals to epsilon into C delta T. So we get the hot fluid temperature as 47.9 degrees Celsius and cold fluid temperature as 32 degrees Celsius. This means the oil is not cooled as much. It exits at approx 47.9, that is approx 48 degrees Celsius instead of 40, and the water exits cooler too and at about 32 degrees Celsius instead of 30. So now we'll move to second problem. The second question says we have a reaction which goes like A gives B plus C, and this is an irreversible and first order gas phase reaction. The batch reactor data tells us that 60% conversion is achieved in 50 minutes. The reaction is to be carried out in isothermal PFR at 400 degrees Celsius and 10 atm. So using the feed is pure A at the feed flow rate is given as 0.05 meter cube per. Find the reactor volume for 80% conversion. This is our target conversion, and we have to find the volume for that. So first we'll find the K value for first order irreversible reaction in constant pressure batch reactor. We have this formula dCA by dt equals to KCA. Integrating this we get this, and substituting the given data we get rate constant as 3.05 into 10 power minus 4 per second. So then we calculate molar expansion factor. Since in this question 1 mole of reactant gives 2 moles of products, we need to calculate molar expansion factor, which comes out to be 1. So after that, for PFR, using the PFR design equation, we'll calculate the volume. First we'll integrate the design equation. The final design equation that we get is this integral of 1 plus x upon 1 minus x into dx with limits from 0 to 0.8 equal to fa naught into v into c naught into k upon fa naught. So using this we further simplify this equation and get v as 109.9 liters, which is approximately 110 liters. The volume required of PFR for 80% conversion is 0.11 meters. Next, moving on to third question. The third question says a Newtonian liquid occupies the space between two large parallel plates separated by a distance b, and the upper plate moves at velocity v in z direction. The lower plate is stationary. Viscosity varies as mu equal to mu naught into e power minus beta into T minus T naught upon T naught. The function is given, and the temperature varies in x direction due to viscous dissipation, and also K and rho are constant. So first we'll look at the A part. We have the governing equation. Let the viscosity equation, viscosity relation, let that be equation number 1. So since the x momentum equation, we have vz velocity component depending on x, that is equation like the z component of velocity is not 0 and depends only on x, and also there is no pressure gradient, so the equation of motion then reduces to d of dx of mu into dvz by dx equal to 0, which means that the inner term, that is mu into dvz upon dx, is constant. That is shear stress is uniform throughout. Next we use the energy equation. The energy equation we can see in the question that there is no convection in x direction. Viscous dissipation acts as a heat source. So the energy equation becomes k into d2ty upon dx square plus mu into dvz upon dx the whole square equals to 0, which we'll name it as equation 3. So the physical interpretation from this is heat generated by viscous friction is equal to heat conducted away. So next we'll move to B part. B part, it deals with the velocity distribution. For that, we'll integrate the equation to obtained in part A. Integrating it, we get mu into dvz upon dx equal to c, which is constant shear stress. Further solving it, we get that is further integrating and substituting the boundary conditions. We get the first boundary condition is Vz at 0 is 0, that is lower plate, which is stationary, and Vz at B is V, that is upper plate moves at constant velocity, upper plate moves at velocity V. After integrating and applying the boundary conditions, we get this Vz by B equals to integral of dx upon mu of x whole divided by dx upon mu of x. The limits are 0 to x and 0 to b respectively. This is our equation 4. This integral form is exact velocity profile for variable viscosity fluid flow. Next, we'll go to C part, which says that it deals with dimensionless energy equation. First, we'll define the dimensionless variables. Theta is beta into T minus T naught upon T naught, and this epsilon is x upon b. So then mu is mu naught into e bar minus theta, and substituting the velocity derivative from equation 4, that is this, into equation 3, we get d2 theta upon d epsilon square plus lambda into e power theta into 0 is equal to 0. This will be our equation 5, and here lambda is mu naught into v square b beta in whole divided by k t naught b square into integral of d epsilon in divided by e power minus theta whole power minus 2, and the limits are 0 to 1. So since the equation 5 is non-linear of ordinary differential equation, the analytical solution exists for this, and integrating it and then applying the boundary conditions, we get the further result. Next, we'll move to last problem, that is fourth problem. It says that two large porous plates are separated by distance b, and lower plate has temperature T0 and upper plate has temperature T1, and T1 is greater than T0. Air is at temperature T0 and it is blown in x direction from lower plate to upper plate with velocity v. Determine the temperature profile and heat flux. So here also we have to find the temperature profile and find out the heat flux. For that,